Hi, this is a quick rundown of Newton's first law of motion, as is self-evident. It's a law that describes how things move, and it was made by Isaac Newton, and it was the first of his three famous laws. Now, modern physics has shown that this doesn't actually work for everything. Okay, subatomic particles such as electrons don't follow Newton's laws, but for anything bigger than a speck of dust or even much smaller than that, Newton's laws work beautifully. They describe how things work, and we can make many predictions based on them. The interesting thing with Newton's first law of motion is that it's quite counterintuitive. You won't. Most people take a lot of convincing that it is actually the way things are. Right, as you can see, this is straight out of the physics new syllabus from 2017. We have this outcome from Year 11 course that says that we need to describe and explain events in terms of Newton's laws of motion. So that's what we're doing. So here we go. We've been doing a lot with vectors lately, so we know that we can have a vector A, that might be, let's say it's a force. Onto that we'll add another vector B, and onto that one more vector, call that vector C. And since you notice that the three vectors added head to tail come back to where they started, and then we can say that the resultant vector is a plus vector B plus vector C, and in this case equals 0. This leads to an interesting question. What happens to the movement of an object when the forces acting on it are balanced? In other words, all of the forces cancel each other out in a vector sense so that the resultant force is equal to 0. Well, Newton had the genius answer that the movement stays the same. Or more precisely, an object at rest will remain at rest unless acted on by an external and unbalanced force. So that's what happens if the object isn't moving to start off with. An object in motion will remain in uniform motion, so that constant velocity, which means constant speed and direction, unless acted upon by an external and unbalanced force. So let's see what that means. Our first example is a rock sitting on the ground. There are forces acting on the rock. For example, it's weight force. And we can say there's lots of little forces pushing up from the ground at the points where the rock is contacting the ground. But if we add all of those forces together in a vector diagram, not a force diagram, but a vector diagram, not a free body diagram, sorry. Okay, you've got W going down, you've got all the little forces going up. They would, we would see that the sum of the forces is equal to 0. In other words, the resultant is equal to 0. So it wasn't moving to start off with, and so it stays not moving. That's called inertia, which comes from the word inert, which means unchanging. Okay. So, what if something's moving already? Right, we have a bowling ball. It's moving with velocity v. Now, at this point, the only forces acting on it, if we ignore friction, because at those low speeds and with a big mass and the hard floor being quite stiff and not being deformed too much, we will ignore friction because it's very small. On the ball, the forces are the weight force, should have vectors, and the floor is able to push back. That's called the reaction. Okay, now those two forces also, boom, weight force down, reaction up. Again, they cancel each other out so that the resultant is equal to 0. Newton's first law says that because the ball is moving already, then it will keep moving. It will keep moving at the same speed and in the same direction until it's acted upon by a force. And that force eventually will come if it hits the pins will push on the ball. But what about the hand? What about the bowler who rolled the ball in the first place? I'm glad you asked. Okay, there was initially a pushing force from the hand on the ball, but that force isn't there anymore. Right? The hand is no longer pushing the bowling ball. So we can get rid of that. And the only forces acting on the bowling ball are the weight force down and the reaction from the floor up. I found this nice little picture on the internet. An excellent description of Newton's first laws. Newton's first law, okay, that law of inertia. With no outside forces, this ball will never move. So its velocity is equal to 0. Then the second ball with no outside forces, right, we see that arrow representing the initial velocity. This object will never stop, okay, because you need a force to stop it. And our everyday experience is that balls roll to a stop. And so this is why Newton's first law is so hard for us to accept. But the thing is, in the real world, there are little forces pushing back. Forces of friction, forces of air resistance that are pushing back against the motion of the ball. And those forces, as we will see in Newton's second law, do cause a change in the motion. But to recap Newton's first law, if there are no unbalanced forces, in other words, if the resultant is equal to 0, then there is no change to the motion. Things stay inert. They stay as they are. Okay, that's it. Hi, here's a quick rundown on Newton's first law of motion. So called because it's the first of the 3 laws of motion made by Isaac Newton. As we can see here, that in Physics 11, we need to be able to use Newton's laws of motion. But first, a quick recap on vector addition. If you look at the 3 vectors, see the arrows for A, B, and C. They chase each other around in a circle or a triangle. So if you add them head to tail, you end up back where you started, a bit like chasing your tail. In other words, the resultant of adding the three together is 0. Now, that leads to the question, what happens to the movement of an object when the forces acting on it are balanced? In other words, the forces have a resultant of 0. There is no unbalanced force. The resultant force is 0. Good question. The genius of Isaac Newton was that he realised that the movement of such an object stays the same. Here's a good old-fashioned quote of Newton's first law. An object at rest will remain at rest unless acted upon by an external and unbalanced force. In the next part, an object in motion will remain in uniform motion, that's constant velocity, which is constant speed in a constant direction, unless acted upon by an external and unbalanced force. So, something that was stationary will stay stationary. Something that was moving will remain moving in the same way. Let's look at a simple example. You see, I've had a beautifully drawn rock, which is sitting on the ground, and there's a downward arrow W representing the weight force, the force of gravity on the rock, and also acting on the rock is the ground. The ground is pushing up on the rock where the rock is touching the ground. Next to that, just here, we see a vector diagram, a force diagram, showing the weight force going down, and then added head to tail, all the little arrows of all the little forces, upward forces, and you see that they again cancel each other out, so that the last arrow finishes where the first arrow started. In other words, that squiggle sigma means the sum of, add up, sum of the forces is equal to 0. The sum of the forces, considering them as vectors, is 0. In other words, the resultant force is equal to 0. So, here, this is an object at rest, which remains at rest because it is not acted by an unbalanced force. Here we have an example of a moving object. You've got a bowling ball rolling along a level surface. The black arrow shows its velocity, v, and the red arrow down shows the weight force, and the red arrow up represents the reaction. So, just next to it, there, we have the force diagram with the weight down and the reaction up, and again, those arrows cancel each other out, so that if you add them up as vectors, the resultant is 0. So, remember, force is one type of vector, a velocity is a different type of vector, so you wouldn't add the weight to the velocity because they're different quantities. It's just like unlike terms in maths, you just don't do it. So, since the resultant is 0, the velocity of the ball stays the same. The bowling ball keeps on rolling, keeps on rolling, keeps on rolling. And that is why Newton's first law is a little counterintuitive. It doesn't seem to make sense because everyday nature tells us that the bowling ball would slow down and stop eventually. We'll go into that in a little while. Of course, what's most likely to happen is that the ball will keep rolling at a steady speed until it hits the pins. And at that point, if we think of the forces acting on the ball, then the pins will be pushing the ball backwards against its direction of motion. And of course, a force against its direction of motion is going to cause it to slow down, if not stop altogether. This picture I found from the internet gives an excellent example. The first ball, it's starting off with a velocity of 0. So if its velocity is 0 to start off with, its velocity will remain as 0 because there are no outside forces. So the resultant force is 0. The second ball, we see the velocity is shown by an arrow. The first arrow shows what its velocity is to start off with, and the second arrow shows what its velocity will be later, which is the same. Remember, whereabouts you draw the arrow doesn't matter. What does matter is the size and the direction of the arrow. So those two velocities are identical. So there's no change in the velocity. Now, why do we think that balls like that, rolling balls, will slow down and stop? Okay, that's because of a number of things. We have these tiny little forces backwards called friction, which is pushing against the direction of motion. We also have another sort of friction, which is air resistance, which is pushing back against the direction of motion, which has the effect of slowing things down. So yes, even though things in the real world do slow down, they still obey Newton's first law of motion. So to summarize, an object will remain at rest or in uniform motion unless acted upon by an unbalanced external force.